Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. In this lecture, we will continue with our discussion of the mechanics of cellular solids. In the last lecture, we discussed about the minimum solid area approach for modeling the properties of composite for cellular materials. We discussed that this MSA model is a very powerful model which can predict the properties of cellular materials over a wide range of porosity, and also depending upon the pore morphology, that means the pore isotropy and the pore shape, it actually predicts different dependencies. And we also showed some experimental results where the MSA model predicts the mechanical properties quite well for its dependence on the porosity. After that, we discussed about the Gibson-Ashby approach to predict the mechanical properties of cellular materials, and we learned that this Gibson-Ashby model is actually valid for materials with more than 70% porosity, that means the truly cellular solids. And this Gibson-Ashby model is kind of it is able to actually predict the mechanical properties of different cellular materials differently. That means it can treat the honeycombs or the open cell forms and the closed cell forms as different materials. And we learned in the last class about the basics of the mechanical properties of the honeycomb materials. In this lecture, we will go into much more detail into the deformation behavior of honeycombs. We will study the deformation behavior in the in plane direction and also in the out of plane deformation. That means, in plane compression, tension, and also learn about the progression of deformation in both in plane. And in the next lecture, sorry for the mistake, in the next lecture we will cover a bit about the out of plane deformation of the honeycomb materials. So, the main keywords for this lecture are honeycomb, in plane deformation, compression, progression of deformation, tension, elastic deformation and brittle fracture. The deformation behavior of honeycombs, as we learnt in the previous class, is actually pretty complicated, but even then we can actually classify the deformation behavior into different types of materials like elastomeric materials, also elastic plastic materials and brittle materials. And also the deformation behavior can be differentiated into either under tension or compression. So, as you can see over here, if we take the compressive deformation as our point of interest, this is this curve and this curve. That means, we can see there is a very stark similarity between the compressive deformation of different types of materials, be it purely elastic material, be it elastic plastic material like typical metals and their alloys, or a brittle material like ceramics or ceramic honeycombs or glass honeycombs. What we see over here is that the deformation basically actually shows three different regions, and as you can see over here. So, initially we have, after the material is put under load, that means we have to remember that these porous materials or cellular materials, they are actually almost always they are put under compressive load, because as we know that the tensile under tensile loading, the pores can actually be acting as stress raisers or weakness, and a crack can easily propagate from those pores and actually cause catastrophic failure of the material. And that is why these porous materials, although there have been studies or instances where they have been put under tension, but the tensile behavior of porous materials or cellular materials is not that attractive in comparison to the compressive behavior, which is actually much more studied in literature, and this is also much more relevant to the actual end application. So, what happens is that at different regions of the stress strain behavior, especially under compression, different deformation mechanisms are actually operative, as you can see over here. So, as you can see that initially as we put the sample under load, there is initially, irrespective of whether the material is elastomeric material or elastic plastic material or a ceramic material, we initially always have a linear elastic region. That means, this linear elastic part over here, as you can see over here or also over here. So, this linear elastic part is actually due to the elastic buckling, elastic bending of the honeycomb struts, as you can see, and then this actually continues, and this actually gives a constant Young's modulus of E star as is being shown over here. And then this actually also shows into the deformation behavior. That means, if you see that how the honeycomb actually macroscopically how the honeycomb actually deforms under compressive load, this can be shown in this particular one. That means, as you can see over here, initially we have, this is the first one. So, in image A we have applied a less amount of stress, that means it is only 10% deformation, and as you can already see that in 10% deformation, 10% deformed sample, already there is kind of like the bending of the cell edges, you can clearly see. But then if you even continue to even higher, that means a 30% deformation, as you can see over here in image B, there is then, apart from bending, there is also elastic buckling, because there are different mechanisms actually operative. If it is a kind of elastomeric polymer, in the elastic region you have elastic bending, and then as you move into the as you cross the yield point, so to say, this is so called the yield point, or the so called the elastic limit, like this point over here, or this point over here, or this point over here. Then actually in elastomeric materials, as we cross the as the strain is higher than this point, or then actually we have, apart from elastic bending, we also have elastic buckling in case of elastomeric materials, and in case of your metallic materials, like in case of image C, we have actually additional plastic yielding, right. And in case of ceramic materials, because the ceramic materials, as you know, that the ceramics do not undergo elastic deformation, plastic deformation, they actually are purely elastic material. So, in that case, and they are also very brittle, that means the ceramics, they cannot sustain significant amount of plastic deformation because of their low ductility. So, ceramics actually, as you cross, so initially you have the linear elastic region up to a kind of a high stress value, and then if you kind of cross the point, or your applied load or applied strain is even further, then actually the ceramic actually undergoes crushing. That means there will be crushing of the individual cell walls, and there will be multiple zigzag kind of motion, as you can see over here, and these individual zigzags actually represent that as you apply more and more load, first as you apply, then one of the cell struts may actually break, and these will actually kind of get compressed into the structure, because as the cell walls are breaking, the cellular material is getting more and more dense, and these actually will provide more resistance to further deformation, and that is the reason you can see over here that as you keep on compressing the sample, you see actually over here that this curve is actually getting more and more, the required stress is becoming more and more higher, because you need more stress, because the structure is getting more and more densified, right. And in case of elastomeric materials and elastic plastic materials, like and in that case, so they have a very long plateau region. So, as you can see over here, after this initial point that you can reach over here, you have a very long plateau over which the stress remains more or less constant. So, this plateau is actually it's a very unique feature of the cellular solids, where although we apply a large amount of strain, the stress remains more or less constant. It might actually rise a bit, as is being shown in this image A, with applied, because the structure is becoming more and more denser, and it actually provides more resistance. But overall, it is a more or less horizontal plateau until a very large amount of strain, and this can even reach up to 60-70% of the deformation, that the stress remains more or less constant. And throughout this plateau region, the main deformation mechanism for elastomeric materials is nothing but it is called elastic buckling, and in case of the plastic materials or the typical metals and alloys, it is the plastic yielding. And this deformation actually propagates in the form of some bands. That means, you will see afterward, I will show you some images where people have actually done in situ study of the deformation behavior, that they have actually captured the images of the honeycomb samples at different levels of deformation, and they have showed that how the deformation propagates at different levels. But this plateau region is actually kind of continuous up to some critical point, and after that point, which you can see over here, that after this critical point, the curve actually goes almost vertically upward, And this actually happens because as we actually compress the material, the opposing cell walls, as you can see over in the next slide, you can see very clearly that the opposite, as we are actually compressing along the vertical direction, the material is getting more and more compressed, and then at some point what has happened, these opposing cell walls will actually touch each other. That means, these opposing cell walls will be so much compressed that there will be no more pores remaining between the struts or the cells, and the structure will be kind of compressed to each other. And this is the point which is called the densification, and here you can see that when the structure reaches densification, you actually the material, I mean in the theoretical sense, this material will actually try to reach the instantaneous Young's modulus. If you measure the modulus at this particular point, for truly densified material, the Young's modulus will approach the value of the bulk solid. So, because as we all know that this E star value which is being shown over here, this E star value the initial modulus of the cellular material is much lower than the bulk material Young's modulus, because we have significant amount of porosity in the material. But now as we reach the densification stage, like in the final stage where we are actually compressing the material, we are actually squeezing out all the pores from between the individual struts, the structure gets fully compressed, and at this point actually we end up with, and as a reason of that, the modulus becomes continuously higher and higher and higher, and this actually approaches the value of the bulk material modulus, and this point is called the densification behavior. That means, the typical stress strain behavior or typical compressive stress strain behavior of such cellular materials, I mean you will see the same things, I mean similar kind of behavior also for open cell forms and closed cell forms. They typically have 3 different regions, starting with the linear elastic region, then the plateau region, and then finally ending in the densification region. And another important point is that these cellular materials, they are, I mean we discussed in the initial lectures where we covered the application of the cellular materials, we learned that these materials are actually very much ideal for energy absorbing applications, and this is because of the fact that these materials show a very extended plateau region. So, as you all know, the tensile toughness or the energy absorbed in a mechanical test, it is not tensile, it is compression. So, that is basically nothing but the area under the stress strain plot. So, if you can see over here, in this particular case, because the applied stress is very low, and this actually even at a very less amount of applied stress, this whole area under the stress strain plot, this will be actually your energy absorbed. And that is the reason that these materials at a very less amount of applied stress, they actually absorb significant amount of deformation energy, and by doing so these materials are ideal for packaging applications, because they, in case of any crash or in case of any accident for example, these polymers or these honeycombs or the cellular materials, they can actually be used as sacrificial materials to, they will deform at a constant plateau stress, absorb significant amount of energy. By doing that, they will actually protect the more valuable contents in the packaging by not allowing the stress to be transmitted to the content of the content. Right. Now, this was all about compression. I mean I discussed about the compressive behavior in much more detail, because as I already mentioned, this compressive behavior of the cellular materials like honeycombs or open cell forms or closed cell forms are more practice relevant, while these materials are rarely put under tension, because if put under tension, as you can also see from the tensile stress strain behavior or tensile stress strain plots shown over here, these materials are very less resistant to damage, and because there is a significant amount of void or pores inside the material, which can actually act as an initiation point of the deformation and damage, and these materials can fail very easily at a very low strain under tension. And this is most clearly observed for the brittle tension behavior, where you can see that just like the bulk ceramic materials, these samples also fail at a very low strain and stress under tensile loading application. Now, another important point is we discussed about the deformation behavior of polymer honeycombs in much more in detail in the last few slides. Now, one important point is that, as we already mentioned, that in case of these materials, these cellular materials, one important point is the most important parameter is the porosity of the material, right. So, because we know that the porosity, this is controlled by the amount of porosity also controls the density of the material, and these two parameters, the relative density or the porosity, they actually control the mechanical properties, and this porosity is again controlled by the strata thickness, because you know that, I mean, based upon this honeycomb structure, we know that if we actually take, this is a honeycomb structure, for example, if we just assume that this is a honeycomb structure, then actually I mean one cell of the honeycomb, and then we have, for example, this is the length of the cell, and then this is the thickness of the individual cells, and this whole space is actually basically your void space. That means your rho over, that means your porosity, I mean we already covered these things, is actually a function of your the strata thickness and the strata length, right. And now it has been actually observed that, as we also expect, that as we increase the relative density, that means we have a cellular solid like a honeycomb, and if we compress it, it will actually show the three different regions of elasticity, plateau and densification. But if now we increase the density of the honeycomb, that means we are actually increasing the strata thickness, that means the T by L ratio is actually becoming more. That means T by L, as the T by L ratio is increasing, as you can see from this particular diagram, if the T by L ratio is higher, your amount of pore space will reduce. That actually means that the honeycomb will have a higher density or lesser amount of porosity, and these can actually be converted, this knowledge can be converted into a deformation mechanism map for in plane compression. Again, you remember the in plane means what? In plane means if this is a honeycomb structure, if this is a honeycomb structure again. So, in plane means that we are compressing along this direction or this direction, not in the vertical direction, which will be the out of plane direction, right. So, as you can see that, as expected, as we increase the density of the or relative density of the honeycomb, it will actually approach more the behavior of the bulk solid. That means our initial Young's modulus will actually increase, that means the initial modulus will increase with increasing relative density, and also as we compress the material, also our yield strength will also increase. That means, as we see that this is the case of the minimum. So, this case 1 is the minimum density, then 2, then 3 and then 4. That means, as we move from 1 to 2 to 3 to 4, our density is actually increasing. That means, our T by L ratio is actually increasing. Correspondingly, the Young's modulus or the initial modulus will actually increase. The yield point, the point where if it is a plastic material, the point at which the plateau actually initiates, that will also increase. At the same time, what is happening? At the same time, as the porosity is decreasing, that means the opposite cell walls will actually come in contact with each other at a lower strain. That means, your densification strain will decrease. That means, the samples with increasing relative density, the densification will initiate at a lower strain, and if we simply connect these points, we obtain this kind of a map, and where actually there are different regions have been shown. Again, the three different regions. This is the region of the elastic region, this is the region of the plastic region, and this whole region is the region of the densification. So, what we can conclude? We can conclude that with as your rho, that means the density of the honeycomb is increases, we have the initial Young's modulus is increasing, your sigma y or sigma PL, that is the plateau stress, is also increasing, whereas your sigma d or densification strain will actually be decreasing, and this is the uniform, this is a universal phenomena which is actually valid for all kinds of cellular materials, as we will also see in future for open cell forms and closed cell forms. So, now as I discussed already that several researchers have actually tried to actually find out how a honeycomb material actually deforms when put under compression. That means, how does the deformation actually propagates. So, because the honeycomb structures, as you can see over here, these are macroscopic porous structures. So, this study of the progressive evolution of the pore size or the pore damage is not that complicated. That means, one can even with less amount of experimental effort, one can study how the deformation propagates as a function of the compressive strain. So, as you can see over here, the initial the honeycomb structure is being shown over here, and these points that you can see on the stress strain plot from 0 to 9, these are the points at which the photograph of the honeycomb structure was acquired to find out how the deformation is propagating. So, as we know that initially, as we compress the material, initially from 0 to 0.1, we have the linear elastic region. That means, there is no permanent deformation of the case. But now, as we move from 0.1 to roughly about up to 0.6, we see that there is more deformation is actually occurring. There is more, if you can see the shapes of the cells of the adjoining diagram, you can see that there is more deformation of the cells happening, and also starting from 0.3, for example, in this particular region, in the middle portion, you can see that there is kind of formation of a band structure. That means, you can see that in this point, where actually in this band structure actually more kind of this band is forming, where the opposite cell walls are trying to come more closer to each other, and then this band structure initiates at certain point within the material, and then as we compress more and more, that means 0.4 and 0.5, we see there are multiple bands are forming inside the material, and this band structure, this collapse of the structure, they actually propagate more and more. And actually, this deformation behavior of the honeycomb is also pretty inhomogeneous. That means, had it been a homogeneous deformation, then the whole structure should actually undergo same kind of deformation, right. But what we can see over here is that it is a very inhomogeneous deformation. That means, there are regions which are very close to the band, which are very as you can see over here in this particular region, or in this region where we have significant amount of deformation of the cells, whereas at regions further away from the bands, like over here for example, or over here for example, you have very less amount of deformation. That means, this deformation propagation of the honeycombs is actually pretty inhomogeneous. First, a band is formed at some region, and then this band tries to propagate, and while it propagates, the cells which are very close to the band or the initial band, they actually get deformed, whereas the cells which are further away from the band, they actually remain unaffected. But with increased deformation, that means, with increasing compressive strain, more and more cells they join the bands, and that is why you see in sample in photograph 7 or 8, we see that the complete sample has been kind of has undergone deformation. And in image 9, you can see that the complete sample, because we can see that it has undergone densification, and opposite cell walls have kind of come into contact with each other. So, this is a basically very kind of non-uniform deformation that we can see in the compression of the honeycomb samples. Also, one more important point we can see over here is that in the compressive stress strain plot, the plot actually is not it is not a straight line plot. Rather, we see there is this kind of serrations are there. That means, we see that there is some points where the stress drop happens, then again the stress is increasing, then again there is a stress drop, then again so these are actually there is multiple stress drops and stress rise, drop raise. So, basically this again happens because we have the nucleation of the bands happening. That means, when we apply the stress, at some point we need a higher amount of stress to initiate a band or nucleate a band, because there is resistance from the overall structure. But once a band initiates, then it can propagate even at a lower stress, because it can actually the propagating stress or the propagating band can actually the adjoining cells can join the band very easily. However, to propagate the to nucleate the band at a point further away from the initial band, we still require more stress. That means, again once a band, I mean we apply we require a higher stress to initiate a band, and then the band propagates at a lower stress, but then again we need even higher stress to initiate a different band, and again the band again requires a lesser amount of stress to propagation. So, this way this, and that is why we see that in this particular case we have multiple stress sedations of stress rise and stress drop, and this way the whole structure propagates until the final densification. And again under tension, as you can see over here, the tensile deformation is being shown over here, and you can again see that as we mentioned that in tensile deformation it again I mean again the first deformation initiates at some point at the weakest point, and then again there is kind of a band formation, and then then all cell walls they try to kind of rotate along the direction of the applied load, and this way the deformation actually propagates. In case of brittle ceramics, because there is extremely brittle materials, these can undergo I mean easy fracture, because under applied load I mean one particular point can undergo failure, and that will actually lead to catastrophic failure of the whole sample. Now, another important point is that we already mentioned that these honeycomb materials, because these are inherently non-isotropic or anisotropic materials, because we have different properties along in plane and out of plane direction. But also in the in plane deformation itself, the honeycomb can be non-isotropic. So, just assume that in this particular case, as you can see over here, this is a regular hexagon. By regular hexagon I mean that all these cell walls are of the same length, and also this angle between the cell walls, that means this angle in each, this angle theta in each case, this is also 120 degree. If a honeycomb is like that, then we have isotropy in the in plane direction, that means or in the in plane deformation, that means the properties along direction x1 and x2 they will be identical. That means, it is irrespective of whether you compress it like this or you compress it like this, you have similar deformation behavior. And in this particular case we have only one Young's modulus, that means the Young's modulus is E star, and we have only one shear modulus G star, and we have also only one single Plateau stress is your sigma star. But if we now assume that our honeycomb in the in plane direction also, our honeycomb is not isotropic, that means we have the cell walls they actually differ in their length. That means, suppose we have a honeycomb like this kind of a honeycomb, this kind of a cell structure where the cells are not identical. In this case, if you compress along this direction or along this direction, that means if we this is our one direction and this is our two direction. So, if a honeycomb is having a shape like that with non-uniform cell length, in that case actually we have different values of modulus and strength along different directions, and then even in the in plane deformation the material will have different properties along different directions. And this will again depend upon, I mean how different the properties are along one or two direction. This will again depend upon the parameters of the honeycomb, that means the cell thickness T, the cell length L, and the angle theta. And if we have the simplest situation where we have it is a uniform case, that means all the cell walls are of the same length and the angle between them are also same. In that case we have this simple equation over here which predicts the Young's modulus of the honeycomb, and you can see over here, as we already discussed, that in that case, in case of a uniform honeycomb structure, our modulus E1 and E2 they are also same. That means, we have similar modulus if we compress along one direction or two direction. The same concept is also true for Plateau stress, as you can see over here. Again, if the honeycomb is non-uniform, that means there is the length of the arms along different directions are different, then again we need to differentiate between the Plateau stress along one direction and two direction. However, if we assume it is a uniform honeycomb structure, then we can again use this simple expression to predict the strength of the honeycomb along any direction in the in plane deformation. And in case of brittle materials, if the honeycomb is made of a brittle ceramic like as is being shown over here, when we compress at some point, because there is kind of there is bending moment, and because of that at some point there is a hinge formation over here, and if the localized deformation is kind of pretty high, then the honeycomb can actually fracture at these points, and this way the honeycomb will under compressive deformation it will be kind of crushing together and giving rise to this continuously rising stress strain plot. So, to conclude this lecture, we learned that in deformation of the honeycombs under compression, they typically display 3 different regions of linear elastic region, then the plateau region and the final densification region. We also learned that the deformation of the honeycomb depends upon the density of the material. As we increase the density of the honeycomb, that means the amount of porosity is reduced, we have an enhancement of the initial modulus, we have an increase in the plateau stress, and we have a reduction of the densification strain. And also there are different regions which actually, I mean, in different deformation regions different mechanisms are there which actually control the mechanical behavior. Like initially when the honeycombs are put under elastic load, it is the bending of the struts, and then as we move into the plastic deformation, it's either the plastic buckling or plastic yielding of the elastic plastic materials, or in case of the elastomeric materials it is the elastic buckling, or in case of ceramic materials if it is a brittle material then it is the crushing of the struts. And then as we deform more and more, as the opposite cell walls contact each other, we move into the region of densification, where we approach the modulus or the instantaneous modulus actually approaches the value of the bulk material modulus. And we also learned that the honeycomb material can again be differentiated into the in plane deformation and the outer plane deformation. And again for in plane deformation we learned that depending upon the cell walls dimensions, like whether the cells are of the same dimensions or different dimensions, we have different in plane behavior along different directions. So, the references covered in this lecture are provided over here, and in the next lecture we learn more about the in plane brittle behavior and also deformation behavior of the foams, and also the outer plane deformation, and also we will move into the next type of cellular solids, that means the behavior of the open cell foams and the closed cell foams in the coming lectures. Thank you very much.